Okay, thank you very much. Thank you for inviting me. I'm very happy to be here. My first time in Houston, Texas. Yeah, so my background is in electrical engineering, signal processing, image processing, machine learning. But most of my research has been towards medical applications, using this type of knowledge within different types of medical applications. First of all, let me acknowledge two of my PhD students who have done a lot of the experiments that I will present you some results. So Rune Vetland is working on the digital pathology, urinary bladder cancer, and Luca Tomasetti, who's working with the computer tomography perfusion images for stroke patients. This is a picture of the main campus of the University of Stavanger. Beautiful and a beautiful day, but believe me, it's the west coast of Norway, and the weather was highly unpredictable, and I left a very gray and rainy city yesterday morning, so happy to be here. Well, we are in the middle of a revolution, the artificial intelligence revolution. And some people predict that this revolution is going to have an even greater impact in the way that humans live their lives than the Industrial Revolution had. It's hard to say when you're in the middle of it, right? But for sure, this group of people that goes to a data science conference, we are well aware of the potentials that lies in this use of artificial intelligence for almost any kind of applications now. We already are seeing, or maybe some of those areas where we really see already impact is in computer vision, in natural language processing, in autonomous vehicles. But we definitely see that the artificial intelligence is heading into the world of medicine as well. There is a vast increase in the number of research papers that are published on the topics around using artificial intelligence in medical applications, and also news articles, books, talks like this, with this type of titles, conferences. So the interest both from the research community, from the private companies, from the public community, the research interest is very large. But where are we now? What is the status? So already we are using simple artificial intelligence methods in some parts of medicine in clinical use, like in robotic surgery, in image analysis is already a part of aiding radiologists in their solutions. And we see that in medical administrations, there are many tools coming on the way in, really. And in virtual nursing, simple systems are in place and already in use. But a lot of the artificial intelligence in medicine is on the research table, not in clinical use today. But there is a lot of research ongoing. Like, for example, within digital pathology, I will talk of one of the examples will be from that. Within mental health, within even within genetics analysis for personalized medicine, there is a lot of research ongoing. So, and with remote diagnosis supports using video, so even using your smartphones for capturing something that's happening on a scene, communicating with a dispatcher at an emergency center. So there is a vast amount of research ongoing, and I see that there will be some really interesting things that will be taken into the clinical world during the next years or decade for sure. So artificial intelligence is, of course, a huge topic. So let's narrow it down a little bit, and I will talk, the examples that I will talk about are from machine learning world, and more specifically from the deep neural networks, the specific examples that we talk about. But even when we talk about machine learning is also a lot of different things. And at the data science conference, I'm sure there are people from working with very many types of data and maybe different types of machine learning. We could divide in these three main pillars like supervised, unsupervised, and reinforcement learning, or maybe even your learning can be in between those. For sure, machine learning shares the paradigm that it's using its data, a lot of data, hopefully enough data, to update its computer models, to update the parameters so that they become useful for whatever it is that you're trying to do with them. So learning from data is, of course, the key idea here. Where if that is in terms of unsupervised clustering for big data visualization, or if regression or targeting marketing for clustering for targeted marketing, or regression for forecasting, they all share this, that they're learning from the data. I see that many of the examples that people are publishing these days on AI in medical applications sort of belong in the group of supervised classification-based methods. And my examples will be in this category as well, even though I do acknowledge that there is a lot of other options and possibilities too. So of course, a generic system based on machine learning has some sort of input data, a machine learning system, and your output data. And for medical data, this input data can be biomedical, like CT, MRI, histological slides. I mean, some data that's collected from the patient somehow, or from a person. But it can also be patient data, history, follow-up records, or even sort of like mentioned, using your camera on your cell phone, or even surveillance camera overlooking a operating theater or a resuscitation table, where we are talking about a medical application in the sense like what is going on, are we doing what we're expecting to do, and so on, and not necessarily a diagnosis from biomedical data, right? But I think whatever it is your topic is, I think some sort of domain knowledge is very useful, because machine learning is wonderful and it can do almost wonders, but it has to be tailored, sort of tailored for your application to a certain degree. And to know some sort of domain knowledge about your data, it will make you better equipped to know how to combine, how to organize, and if there's some pre-processing, denoising type of steps that should be applied, and what makes sense if you need to sort of patch up your data. It's important to know you do that without losing what is potentially important information, and so on. Don't filter your data too much too early. That, I think, is important to know. Whereas for the output space, that can also be many different things. But depending on your application, you can have a lot of data, and sort of from that huge amount of data, you're targeting to get one label out. What is this diagnosis, or what is the chance of this patient having a recurrence, or what is the prognosis? But it can also be that you want to map the same dimensions of your input, like an image. You want to have a segmentation map, as illustrated here, which has the same dimension as your input. You can also do even super resolution, if you want to have your output to have an even larger dimension than your input. It's or some other, whatever your application and your data can make sense of. So when you know that, when you have sorted out your input and output structures, then we can sort of start thinking about good types of architectures, parameters. Should this be done in multi-scales or not? Bottleneck structure or compressing, and so on. So there are tons of different possibilities still, and we end up doing an engineering that is around the choices of hyperparameters and architectures, whereas we may be image processing and signal processing people like me. Before, we're sort of thinking like, what is a good feature to extract? So now we're thinking like, let the network extract the features, but still you have to do all these architectures and other decisions around it. I want to talk about digital pathology very briefly in general, and then a specific example. So when a biopsy or a tissue sample is removed from the body, is sent to a lab where it's fixated and cut into very thin pieces and mounted on a glass slide and colored, and everything this is done manually and with a still something that you can't get all automized. But at one point, now the pathologists will study this, or traditionally been studied in a microscope on this glass slide. But in later years, the scanner technology has become very good, and now we can digitize these small tissue slides until a magnification up to 400 times, or maybe even more, but at least the ones that we are working with, 400 times magnification is high resolution. So the minute you have the digitized slides, we call them whole slide images, then you have a whole set of new possibilities. Like still today, a lot of these slides, when a pathologist needs a second opinion and actually send it in a mail to another part of the country or another country even to get a second opinion. Whereas, of course, when it's digitized, we know how easy it is to be able to share as long as we take care of the privacy concerns and all that. But it's not only that, it's also that we can use the digital tools we know, like image processing and machine learning, to help the pathologists in their work with segmentation, classification, prediction, and so on. So not only can we, but we have to, because today the number of biopsies or tissue samples that are sent into all the laboratories all through the Western world is going like this. At the same time, the number of pathologists in all the same countries are going like this. So there's no way we can solve this without having better ways of helping them to do their work more efficiently. And also then comes the question if we can learn from the algorithms as well. We have ongoing research with the University Hospital in Stavanger on urinary bladder cancer and melanoma studies already, and we are very excited about next month starting a larger European project together with hospitals and universities in the Netherlands and Spain as well on cloud artificial intelligence for pathology, where we're actually going to use smart contracts and blockchains and all this in between. So it was fun to hear you talking about that. Yeah, but that's to start up soon. Okay, so urinary bladder cancer is maybe not the cancer you hear about the most, but in Norway at least, it's actually the most expensive cancer type, because there is such a large chance for these patients to get recurrence and also progression. At the same time, the grading is difficult to do, or it's difficult to predict, at least, if they're going to get recurrence or progression. So this leads to an extensive follow-up scheme where they call back like every 3 months or every 6 months and so on. So it's, of course, unpleasant and expensive. And it will be helpful both for the pathologist to sort of make the workflow a bit more efficient, but also hopefully to say something about the danger of recurrence and progression, and if the danger is low, maybe the follow-up scheme can be a little bit less tight and so on. Yes. So as a part of the project that we are doing now, we want to do a full tissue classification of the entire whole slide images. And the reason for that is that there is different tissue types on the slide, even if it's a small small biopsy, and we have the type of tissue that is diagnostically relevant. In this case, it's the urothelium. But then we also have these tumors are removed with a laser, so there is always some burnt, damaged part of the tissue. There is some muscle or stroma and blood or background that you're not interested in. So we want to segment the entire whole slide images to get the interesting tissue, to feed them into another network for diagnostic and prognostic prediction. And we have some work on that is published, some in review, and then we have some preliminary interesting results on the diagnosis and prognosis as well. But right now, I'm just going to talk about the tissue classification. So these images are huge. Like I said, there's a 400 times magnification and with high resolution. So they are at the sizes of approximately a gigabyte, 100,000 by 100,000 pixels or something like that, right? So they're huge. They're pre-stored in a pyramid fashion with different resolutions. And that might be different from different scanners, but at least the images that we are working with have this with 400, 125 that is sort of pre-stored resolutions. And a truth marking, a complete truth marking on all the tissue in that slide is extremely challenging. I don't know anybody who has whole slide images where they have had absolutely all the tissue classified and marked. So it's not something that we can expect to be done. It will take the pathologist hours to do that for one, and they don't have time for doing that. Like I said, the number of the biopsies and the number of pathologists, they're all overworked. So what we have to deal with is weak labels. And I think that's something that we're going to have to deal with in a lot of medical applications. So with weak labels, I mean that weak labels can mean different things, but why I call it weak labels here is that we have, first of all, we have a small set that is labeled and many that is not. And the small set that is labeled is maybe just labeled at the 400 level that the pathologists have sort of circled around small areas and saying everything inside here is definitely this tissue type, everything inside here is definitely that tissue type, and so on. And when we go up, if you look at the same number of pixels, patch size in different levels, there would be including more than one group. So, and that's the best we have, that's what we have to work with. And then when it comes to the prognosis, we know the follow-up information of the patient. We know if they have recurrence or progression. But that we have to base on just the whole slide. Yes, there were recurrence. Yes, there were progression. So our problem, the way we are attacking that is going through these different layers of trying to find the diagnostic important areas first, and then we can try to do the prognostics. So I'm sure there are many here who are working with different types of neural networks and so on. What we did here is we have weak labels and we have not enough of them, so we have to do some sort of transfer learning. And here we're using BGG16 networks that are trained on the ImageNet data, which is definitely not pathology data. But we use them as a feature extractor. We throw away the fully connected layers and add on our own. We use one for every of these 3 scales. And then we play around with different possibilities. Are we only training or classifiers? Are we unfreezing the feature extractors and train everything? Are we using just 1 or 2 or 3 of those magnification layers and so on? So we end up having quite good results when we're looking at only our small label sets. We get quite good results with everything we try with this type of learning. But what really matters is how it works on new whole slides. And this is an example where I have the image to the left, and to the right is overlaid with a heat map of what we believe to be the urothelium class. This is the damaged tissue, and this is the stroma tissue. And these are considered by the pathologists we work with to be very good results. And then here's another one where we try to do a full segmentation map out of that. So we are combining those different outputs and thresholding them and putting them back in again to a full segmentation map. See the resolution in my output map was not the best here, but to put on this big screen. But you get the idea, right? And here you actually see the green part there being a muscle, which turns out we thought we are only wanting the urothelium, but then our pathologist telling us that's really useful information, because that says something about that the tumor has gone down in the muscle area, or what they have considered to be the tumor when they removed it, and that is another grade, is a more severe grade than if there is no muscle tissue there. So that's something they really wanted to know. Yeah, okay. So that sort of finished that example, and now I want to talk about a completely different example, but how we can, again, use neural networks to solve another thing. So here is an example of computer tomographic perfusion images for detection of cerebral stroke regions. So there is more than 13 million people that suffer from ischemic cerebral stroke every year worldwide. And a thrombolytic treatment can reduce brain damage, but there is a narrow treatment window for that. So that means that has to start within just a couple of hours, or the brain tissue is dead, and when it's dead, it's really dead. There is nothing you can do with that. So CTP imaging is the most used primary assessment tool, and according to the radiologist that I work with, she keeps saying that time is brain. So here, when a patient comes into the hospital in Stavanger, where if they suspect stroke, it's the first thing they do is the CTP, and they really want to assess it as quickly as possible with that. And if there is something to save, then they go on with treatment. But if the patient comes in too late and the tissue is already dead, then there is no reasons to start with a both expensive and potentially harmful treatment. So then they need to consider it. So what I need to know is how much of that area, well, with a stroke, there is a thrombus, so that there's an area of the brain that doesn't get enough oxygenated blood. So this area will eventually die if you, not the person, but that area of the brain will eventually die if it doesn't get re-oxygenated. And the core is probably dead already by the time you come to the hospital. But the area that might be saved is what they call a penumbra, or tissue at risk. That's what we really want to know. Is that a part that can be saved? So then they should start the thrombolytic treatment. And the CTP is computer tomographic. When it's perfusion, they do this 3D scan of the area of the head, but then they do it many times in time. Yeah. So it ends up as a 4D data set, where time is the fourth dimension. And they are injecting a contrast fluid so that you can see how that contrast is perfused in the brain tissue and then washed out again. And if you see that one-dimensional curve at the bottom is for one pixel in one slide followed through all the time points, you see that the Household unit, or the gray level intensity, if you want, is sort of rising and then disappearing or vanishing out again. And from that, in the machines that they use at the hospital, in the clinic today, they automatically extract some parametric maps based on that. So the time to peak, the slope of that curve, and so on. It tells the no, not the pathologist, no, it's the radiologist, how to interpret this. So based on these maps, the radiologist will sort of say, oh, there is a core, there is the penumbra, and so on. So There is, of course, many research groups who have suggested ways to sort of do that thresholding automatic. And then they base their truth markings on or most of them, on dynamic weighted imaging, which is done a bit later. But remember what I told you, like this is a process where this area of the brain is dying fast. So if you are basing your truth marking on something that is done a bit later, then what is penumbra or what is core is not really well defined, or the truth marking is not maybe right, it's biased. And also different, in literature there is a lot of different things that have been done so far, but based on the parametric maps. And we kind of suggest to go back and out of the way of thinking that don't filter your data too much too early, which there are many examples of that tell us that this is a good way of thinking. So you need to know what to filter and how to organize, but don't remove too much too early. So we go back to the 4D CTP volume, and we are not looking at the parametric maps at all, except that the radiologist has looked at the parametric maps and done manually tracing of what she believes is the core and the penumbra based on that, but that's based on the same time point as what we are looking at. And so that's our input. And yeah, this is sort of just going to talk about what we tried to do with this outline here. So we take, first of all, we do some pre-processing because the patient can move the head a little bit during examination and so on. So we have to do some image processing step here. We have to do a register of the images, removing of the skull, some of contrast enhancement, and then rearranging them. So that's done first. And then we look at the whole, do it slide by slide for now. We're thinking of doing the whole 4D as input later, but for now we've done it slide by slide, so it's 3D because we do the whole time dimension in our input structure. So we do it 2D in space, but 3D because we have the time as a part of the input. And then through a UNet, or not a UNet, but similar to the UNet architecture, for those of you who are familiar with that, and that sort of is a bottleneck structure. So it's a compress your data and then expand them again. So back again to, spatially, our output has the same dimension as the input, but the time dimension is removed. So now we get a segmentation map directly that gives us the core, the penumbra, and the brain that is not damaged, at least not so far. Okay, so this actually, they gave us, we were surprised of how well it worked. So we were very happy with that. But let me just say, it's a small data set for now, and it's also with large strokes. So we need to generalize it. We need to see how well it works with bigger data sets. But to be as fair as possible, we did complete cross-validation with a leave on a patient out level, right? So, and also we've done data augmentation not on the test, but on the training set and so on. So we see it as a proof of concept with promising results, not to pay too much attention to the numbers in the results, but more that this seems to be a very good idea, and we are planning to do that. And we are now starting up, the student was doing his master on this, has now started as a PhD student, and we have a medical student starting as a PhD as well. And we're trying to do, they're going to do this twin PhD project with both a medical and a technical at the same time. So we're a bit excited about that as well. So to wrap it up, skipping those first there, but I just want to say something about this challenge with medical data. There is big challenges with the data access and the privacy concerns. I think the GDPR is really nice that has come because now it's not just in the medical world we have to think about that, it's through everything. And that makes all the data scientists aware of these problems and issues and boosts the developments and possibilities that gives us. Distributed learning at the hospitals and just sharing the same models is of course one thing, and continue learning on others' models and then sharing the model again. Having models in the cloud but data on different areas is one thing. Smart contracts and blockchains and ways to share data is other ways. And then there is never enough labeled data, and that's absolutely never going to be enough labeled data. So somehow to deal with weakly labeled data or to deal with training without having, like really well-defined labels and so on is also going to be something that needs to be looked into more by more researchers in the future. And can it be trusted enough? Can machine learning be trusted enough for medical applications? Well, we are trusting our lives for automated system whenever we set ourselves inside an airplane, or, there are so many times we do that without even thinking or blinking. So yes, I believe it should be, but medical doctors are conservatives for good reasons, and should be too. So maybe this whole idea of explainable AI is important, and not only to increase the trust level, but also because I believe that we can learn from the algorithms as well as we learning the machines with our inputs. And that concludes my talk.
Let's thank our speaker again. While we're switching, we have time for one question, and we have one here, so we'll do that.
I was very curious about the first example that you showed with the histopathology, learning from weak labels. Do you have any strategies for validating the results?
Yeah. Which is a very good question. So for now, we have had a pathologist looking at the segmentation map side by side by the histological slide, and sort of saying like, yes, this looks very good. But that's not a very good way of validating, and we would love to have a better sort of like quantification of that result. For now, I don't have a good way to validate that better than sort of like him saying that. But what we want to do, well, since our next step is to use those regions from the urothelium tissue to predict the recurrence rate and the danger of recurrence and progression, I'm thinking that if that gives us good results, that is in one way of validating the whole process, right? Because there's no way you can just feed the entire slide in and expect to get a good prediction on grade or recurrence, since there is too much noise in there. There is too much damaged or... So I'm thinking that's one way of sort of validating your results is indirect, but again, with weak labels, I think maybe you need some sort of indirect ways of validations.
Let's thank our speaker again. Thank you.